Let's get started then. Thank you for coming. Today, we want to talk about the AutoML essentially. So we coined the term use AI to build AI before AutoML becomes popular. AutoML was primarily used by Google to describe the similar technology. But the idea behind our technology and Google's AutoML technology is kind of similar. But the algorithm, the actual implementation are quite different. I will show you how technology has evolved in this area in the last, primarily in the last 2 years, and explain the difference between our method and Google's method. This is kind of new, so I hope you will enjoy the talk. Do you guys hear the echo, or is it just me? I found it's kind of annoying. Okay, so a little bit about myself. So I'm co-founder of OneClick.ai. We build an automatic platform that creates deep learning models for you as a fully managed platform. Before we started our own startup, I was a dev manager at Microsoft. I worked on Bing IS relevance, Bing logo search, and map auto-suggest. So I think I had about slightly over 17 years of machine learning experience. During my work at Microsoft, I gradually realized most of the things we have done can be automated. Though without automation, it took hundreds of people at Microsoft Bing to build those machine learning models. And that's our daily life. But most of the time, I see people are making the same mistake and using similar technology to improve different problems, to solve different problems. So if we can find a way to figure out when to use which technology, we can automate the entire thing. That's how we started to think about AutoML. In reality, it's getting more and more complex as we started building the system. But this will show you high-level idea that we have. So before we run into technical details, I want to explain why we think this is a valuable thing to do. It's worth our time. So the slides here show you some of the technical reasons why people would need AutoML. The supply of data scientists is limited compared to the demand in the market. That's why basically the salary of data scientists getting up every day. And doing machine learning is generally more difficult than traditional software development. So especially if you see it as a software, it's as complex as any software, and it's dealing with numerical data. And you need expertise on machine learning, so it's more complex, taking much longer time to deliver anything. That's why even at Microsoft Bing, at that time, we have great engineers, but we still deliver the first version of every project using only rule-based engines instead of machine learning. So machine learning is also unpredictable. You don't know on this particular data if a method works or what you want to achieve can be achieved at all. It's hard to predict that. So you may find that the project fails after, let's say, a couple of months building a machine learning model. And when it comes to actual implementation, integrating into the real system, there are lots of engineering traps. And because we are dealing with numerical data, it's hard to debug, it's hard to verify its correctness. But besides all of those, that's one key point I want to explain. That in the US alone, more than half of the business generated revenue is actually generated by small businesses. And The definition of small businesses varies depending on your opinion, but I think the government's definition is very simple. If you hire anyone outside your family members, you are not small business. Think about half of the entire U.S. revenue generated this way. Can you imagine those businesses who can only hire their own family members to hire a data scientist and pay them $200,000 or $300,000? So that's basically tell you why education alone cannot solve this problem. They cannot make AI accessible to the community. Just by education, by building better technology, you have to automate machine learning. That's the only way to go. So nowadays, deep learning, in many ways, deep learning is the reason that machine learning becomes a hot topic those days. But deep learning actually brought more challenges to the people who apply machine learning. So I'm not going through the list, but that are just a few I could think about. So what's AutoML? At a very high level, AutoML is the process. Think about it, you have a controller. Think about the controller as a data scientist who designed the models. So the controller generates a model design. That model design may involve, here we're talking about models in a very general sense. It may include feature engineering, feature selection, data cleansing, and you have to choose an algorithm or design your own specific algorithms. And you also have, if any other things you have to do as a data scientist when you design the solution, you also have to do here. So once you have the model design, you move to the next step. So you use the actual training data to build the model. After that, as a data scientist, you would evaluate your data using validation set. Some people call it a test set, but here I just want to be very specific. It's validation set. The evaluation result on the validation set will be used as a feedback to the controller. Think about the data scientist. I will review the validation results to see how well my model performed, and then I will modify my model. And hopefully the modified model is a better one. That's exactly what this controller does, except the controller does it has to do it automatically. That's the only difference. So the key challenge to the controller, because the rest of the process, except what happens inside the controller, is the same thing just as a human data scientist. So the key challenge is I'm referring to the controller. Number one, you have to design reasonable models. Otherwise, your model won't work. You can't even train it, then it's useless, right? That's a very basic requirement. But the key thing is the first model you design may not work well. So you have to be able to take the feedback and translate it into an improvement to your model design. But how do you do that? The feedback can be, sometimes it's just a single number saying, let's say it's a classification model, then you may evaluate the model using accuracy. And the first model you design has a bad accuracy, like let's say 20% accuracy. It's very bad. So how do you improve the next model that you design based on this particular feedback? It's just a single number, 20. How do you improve on that? Also, because it's iterative, it's an iterative improvement. You have to go through this process many times. So you have to think about how to reduce the number of models you have to design and you have to train. Designing a model might be fast, but training the model is typically not really fast, especially when it comes to larger data sets or when you are dealing with images. Also, there's a problem called local minimum. So typically, machine learning problem can be thought as optimization. And in optimization, you are trying to find the best solution. And But often, because of the wrong assumption you had, you found secondary solutions, which prevented you find the best solution. I will give you an example later. But a typical scenario is because you had bad assumption, then all the models you designed will have that assumption built into it that prevent you testing other options that you might have, but because you believe those models are bad models, so you never tried them. Because you never tried them, you never learn you have made a huge mistake. So there's no feedback for you to correct that. So this had to be addressed so that you can actually iteratively improve yourself. And the model training is slow, especially when it comes to image classification, which is the example used in this talk. So it may take tens of hours, even on class of machines, GPU machines. So we got to find a way to speed it up. Otherwise, it's simply too slow. So the rest of the talk will go into technical details as to how the controller is designed. And I'm basically using some of the published research from Google to explain how AutoML works and how it has evolved in the last 2 years. Greedy search is definitely not the first AutoML algorithm published by Google, or in this particular line of research. But it's a significant one because the latest release of Google AutoML as a product was powered by this particular algorithm. This algorithm, also the Google product built on top of this algorithm, was focusing on image classification, and this is the only thing it does. I will go through some technical details before I explain the pros and cons. So it's not, let me say, the model designed by this algorithm is not very generic. So there are lots of assumptions about what model should look like. The reason they come up with those assumptions because image classification is a well-studied topic. So people have experience building solutions on those data sets, so they know what could work, what wouldn't. So that's why. So they designed 2 different neural net architecture. Here, the first one contains up to 5 cells. I'll explain what are cells. But some of the cells may repeat multiple times, but the other parameters are all fixed. So the task of AutoML or the greedy search algorithm built into the controller is to find the best design of the cells. Because the overall architecture, once the cells are defined, the overall architecture of the model, the deep learning models, are fixed. So, okay, so now we explain how to build cells. The cells let's say, contains a set of neural operations. It's constructed from very basic constructs, very basic units here. Each unit contains 2 operations, and then combine their outputs together. Those 2 operations are sometimes very simple operations. Can be fully connected net or just one layer of convolution. So typically they're very simple. And if you for those who are not familiar with neural net, they can be translated into simple addition and some nonlinear function, like for example, sigmoid or a ReLU function, a cutoff function. So the mathematical form of those operations is relatively simple. So when we talk about design a cell consisting of some of those operations, we're talking about let me say it this way. Each component contains up to 2 operations. So you have to decide what are the 2 operations you want to use, and what are the inputs to those operations. Once you decide those things, you have basically you have this construct defined, and you can define up to 5 constructs like this to construct a cell. So you actually have Google designed it this way so that you have limited number of choices, so that we can keep things simple. Those are the 8 options that you have for the operations. You can put any of them into operations and use the output of previous layer as an input to those operations. So let's take a look at this example. This is a real one. So this is what we call construct, or basic component. So you have input from this layer as output from this layer as input to this one, and this operation is a 3x3 convolution, I believe. And so you in this cell you have 5 constructs. This 1, 2, 3, 4, 5, and those are and here are the inputs of the previous outputs of previous cells. So you chain those outputs together and feed them into this layer as an input. And then you finally combine them all together to produce the output. That's basically what does neural net look like. By this design, with all the constraints I described earlier, we have up to this number of designs. Because the rest of parameters are fixed, so if you have this number of cell designs, you have this number of neural net design. So because the number of designs are fixed, so you can translate this problem, optimization problem, into a search problem. Basically, you start by construct cells with a single construct, and then add more construct to it, to gradually build up a more complex cell. And here we are limiting the number of constructs in a cell to 5. So when you talk about single construct, there are 256 options. This is the number that we can manage, so we try all of them. We generate the cell design, then generate the neural net design, and we build the models. And it may take, let's say, tens of hours to build each model. But Google certainly have enough machine power to build all those models in parallel. Then you pick the best. You pick the best K cells. And because in the first round, the K is a small number, so you can actually do all of them. But in the next round, when you add another constructor to the cell, the number will be much larger, so you cannot train all of them. That's where you want to use the machine learning algorithm to figure out which cell might deliver better results. So you only train those models instead of training thousands of models altogether. So by adding more cells to the by adding more constructs to the cells gradually, we build up to 1,000 models, and we train those models to figure out which one is the best. So in order for this algorithm to work, the key things that you have to do right is to predict which model need to be trained, because only the models that you actually train will be shown to the user. So that is done by another machine learning model. It's actually a deep learning model using LSTM. LSTM is a type of neural net. It's called the recurrent neural net. It allows you to take in different parameters, and here the parameters describe the model. For example, the parameters tell you which input you want to use for construct, and also it defines the operation you want to use in each construct. Then the definition of inputs and operations is just like a sequence of data. That sequence can be fed into the recurrent neural net so that the neural net will produce a result, a prediction about the accuracy of the model, as if you actually trained it. This is a very relatively simple model, but it did a very good job of predicting the accuracy before you train the model. With such an algorithm, I sometimes call this a meta-learning algorithm. With this meta-learning algorithm, they were able to figure out which model was further developed to add new cells, new constructs into it. Using this method, this is essentially a greedy search algorithm. Using this simple strategy, they were able to, let's say, train fewer models and get much better results than all the previous AutoML algorithms. And actually, the result is better than any human-designed algorithms at the time. It used lots of heuristics, as I have shown. Those heuristics are based on the knowledge of humans who have accumulated over the time when they do research for image classification problem. It's a well-studied area. But they also use heuristics to try to build simple models first and then grow the complexity over time. So that they can stop earlier. And of course, even they limit the number of constructs in a cell to 5. That's also heuristic because they believe they don't need more complex models. So all those things, when you add them up, I can simply say the model, the algorithm designed this particular way will work for image classification, but there's no chance this can work for other arbitrary machine learning problem. If you switch to a different problem, for example, let's say you want to build a topic model to classify text, natural language text, then this algorithm won't work at all. They probably won't even run on such data set. So, so that's the key thing. The algorithm cannot generalize. What it means is if you want to build such an algorithm to automate machine learning, to solve your own problem, not image classification, of course, then you have to design your own. You have to design your own AutoML algorithm, which is often more complex than image classification or other problem you are trying to solve. So basically, you translate one problem into another more complex problem. So that's why it's not a solution. So Google later, actually earlier this year, showed another algorithm that is a little bit more promising. This algorithm is based on reinforcement learning. So the basic idea is instead of doing a search between different algorithms, you use a model to generate a specification for the algorithm that you are designing. It's a generative model. It directly generates the model, so there's no search involved. The reinforcement learning algorithm is more generic. It can take different forms of inputs, generate different forms of output. So it's easier to write and to develop if you want to use it to different areas. Basically, to solve problems other than image classification. Okay, so this is what it looks like. This is the controller. Remember, the controller is the one that designed the model. Ignore the details. The controller basically generates a sequence of outputs. Those outputs defines the parameters and the number of layers in the model. So, for example, those are the parameters of one layer: the filter, the head, width, filter. Those are basically all the parameters you need to define a convolution layer. So if the controller keeps running, it can generate an arbitrary complex, can generate a neural net of arbitrary complexity. So to generate another layer, you just run it more iterations to generate them. The basic idea of this is, let's say advantage of this is that you can use an RNN controller. You can describe any arbitrary neural net architecture, at least in theory. So that makes this algorithm a lot more generic. So you still have to, let's say when you want to solve a problem other than image classification, you can relatively easier write a new algorithm using this. Because any neural net can be described as a sequence of parameters. So this has the ability to define any neural net in theory. With some modification, this model can generate more complex models by doing something we call the skip connection. So I'm going back to the previous slide. So this basically means the output of previous layer is going to be fed into the next layer in this design, because the inputs to each layer is not defined in this neural net. But sometimes neural net can be nonlinear. Basically, it's more complex, like a graph. So the output of a layer may not be used by the consecutive layer, but maybe after 2 layers, you may combine the previous output as the input. And in that case, you have to have a way to define which output you want to use as the input of the current layer. So that is addressed by this something called skip connection. Basically, you output a parameter that tells you which output generated by the previous layers should be used as input of the current layer. So with this, reinforcement learning can generate designs for very, very complex models. So this is great, actually. But to actually make it work, just for image classification, you have to make some assumptions to build in heuristics that humans have learned over time. For example, in theory, the parameters should be any arbitrary number, arbitrary integers. But that would mean there are too many choices for the model. It's too complex for the reinforcement learning to learn in finite time. So they limit that to 4 choices. There's no magic to those 4 numbers. But those are based on human experiments. But based on my experience, those numbers work. That's why I chose those numbers. So that's why I didn't choose 1,000,000. I didn't choose 1,000. I didn't choose 1 or 0. Because those are the numbers that historically worked for the same problem. So you can imagine if I switch to a different problem other than image classification, I won't have the magic to come up with the right numbers here. That's the problem of this. So also for other parameters, there's also a limited set of values you can choose from. So that makes things a lot easier to reduce the number of choices you can make. But one thing they did is, as I mentioned earlier, without paying special attention, sometimes your algorithm has a wrong assumption about what kind of model will work. With the wrong assumption, you tend to generate a model that you believe will work, but leaving other options unexplored. As a result, you may not have a chance to correct your mistake, because the best model, you thought the best model is not worth trying at all. So, in this reinforcement learning algorithm, what Google did was to generate a distribution to say this model has better chance to, let's say, to perform well on this data set. That another model may have less chance, but it still have a chance. It's probability. I don't know for sure. I don't know its accuracy for sure. So with some smaller chance, I would still try the better design. I believe it's bad, but I don't know that for sure. So let's say I use if I train 1,000 models, I may use, let's say, 200 models to try the bad ones. But by doing so, because I actually built the bad ones, the ones I believe are bad. So if it turns out those models are good, I will learn I have made the wrong assumption. So this provides feedback so that the controller can learn my assumption is wrong, I should change my assumption and penalize my assumption. By this way, it corrected its own mistakes. So that's how it found a way to avoid building secondary models. So the training of the controller is based on standard reinforcement learning algorithms. I'm not going to the details of the formula, but basically it takes the feedback of the accuracy. So basically, because you train the model, you actually know the accuracy on the validation side. So that's the feedback number. Of course, the validation is higher. The validation is higher, the better. So if the accuracy is low, you get a huge penalty, or you try to change your design. If you build a correct model that actually have better accuracy, then you know you did something right. You will keep doing that to in your new model designs. By doing this way, you basically figure out which kind of design, which kind of component you have tried before that would can work better. Okay, so another trick implemented in Google's implementation is when you have many models that share the same construction, similar, let's say, similar parameters, you can actually share those neural network constructions together, so that you don't, let's say. So without this, basically, if you have two different designs of neural nets, you have to restart training from scratch. That, let's say, they take a whole day. But if those two neural nets share some of the components, you can combine the two neural nets together and train them together. This is how they speed up training. This helps a lot in certain cases, but unfortunately, because the neural net generates parameters automatically. So often, if you take two random models designed by the controller, they don't share much in common. That basically say this algorithm in practice won't help you a lot. Okay, here's a summary about the reinforcement learning controller. So it's actually delivers a better model in experiments on the same image classification problems. Those models are better than the greedy search one, and certainly better than the best models humans have designed. Because it's using reinforcement learning, it can be easily generalized to other problems. But with certain conditions, because to make it actually work, you still have to limit the options to very few. For example, for each parameter, as I showed, Google limits it to up to 4 different choices. And you have to somehow magically figure out those choices. Otherwise, the algorithm still won't work. And using those things and some other tricks, Google was able to speed up the training process. So the greedy search actually used like 40,000 GPU hours. If you actually do this training yourself on AutoML or on AWS, this would cost you about $40,000 US. But using this reinforcement learning, they were able to reduce the computation hours to 16 hours. That's a lot faster, a lot cheaper. But unfortunately, it happens only when the neural networks share the similar structures. So if they don't, as in the general case, this won't happen. So, but still leave a very big problem, as I mentioned earlier. So the algorithm, the controller, still have to be specifically designed for your problem. The current one that Google designed works for image classification. So the output of the controller will be interpreted in certain ways to be translated into neural network design. But if you are working on different problems, you have to redesign those things. And also you have to magically figure out the right parameters. So it's not generic enough to solve a general problem. But we are trying to build a platform that solves general problem because we never get a chance to see the data you upload to our platform. And they tested on different data sets, but on average, you still need about 10,000 GPU hours, which translates into a cost of $10,000 US. We believe this is still way too expensive. Though right now, if you if you are lucky to get a trial account on Google AutoML, they only charge you $500 for this. My account hasn't been approved. I think partly the reason is that they have to limit their cost. So what we can do, because we were building a more generic system, we need a more generic algorithm that can work for pretty much any data set. Definitely not limited to image classification. Otherwise, it's pretty useless. And also, because we want to make this available to everyone, including small businesses. So it got to be much cheaper. So the cost couldn't be $10,000 US. So by making it cheaper, you actually need to make the algorithm run a lot faster. You need to train fewer models. How do we do that? And sometimes for some data set, neural net won't work. For example, if you have a very small data set, a neural net just simply won't work well. In those cases, you have to fall back to traditional machine learning algorithms, like decision trees, ensembles, or even linear models. But the AutoML won't help you in those cases. So how do we, let's say, automatically build an algorithm that work with the linear models? You basically, if you do it manually, you actually do it by improving feature engineering, by adding new features. But this is not something Google AutoML can help at all, because it only works for neural net. And there's also a huge problem with all the algorithms that you have seen, greedy search or reinforcement learning, is the first model and the designs won't work at all. Because if you look at the flow here, the flow chart here, so in the original design, the controller has no input. When it generates the first model, it doesn't take a look to your data. Think about a data scientist designing a model for you without looking at the data and without knowing what problem you are solving. The first model guaranteed not to work at all. And even the reinforcement learning is smarter than the greedy search. Because it doesn't, all the feedback it takes is just single numbers in the accuracy. 20% accuracy, 50% accuracy. But how do you use think about how much information you can get from single digit, 0.2, 0.4. You won't get much information. So essentially, in the first thousands of models that you designed, you just randomly try it. And eventually, you will have the luck to see one or two models start working better than the previous models you built. That's where you can start learning things. So this learning is going to be very slow. That's why you need to train thousands of models in order to learn what kind of design works on this data set. So that's why it costs so much and takes so many GPU hours. So to address this, we actually add the training data. I should correct this. This is validation data, not training data. We use the validation data set as a guidance to the controller. So guidance for the controller, take a look to the validation data set first. the easier way to think about this is look at the statistics of the data set. And then based on those things, I figure out what should be the best model that I can design. And then I design the model and actually train the model. Once I train the model, I still do the evaluation using the same validation set as here. It's the same validation set. So then you feed back the accuracy to the controller. By doing so, you actually turn the controller into a supervised learning problem. Your input is your training data. Your input is your training data, and then your validation data, and then you produce the output, for which you have a label. The label is as accuracy, evaluated on the validation side. What this allows is because the supervised learning allow you to generate the output directly from your input. So you can remember for what type of data, what kind of statistics, what kind of technology should be used. For example, what kind of algorithms should be used, what kind of feature engineering should be used, what kind of features I should generate, and what kind of neural net architecture or what kind of parameters can work better on this type of data. That's what you can learn in the controller once you turn it into a supervised learning problem. Because that allows us to build the first model that works on the data. And the first model typically works much better than what could be generated by reinforcement learning, which is just throw out a random design. This is what makes this algorithm a lot faster. And also, because we have the input is validation data set, then that allows us to get more information from the feedback loop. Sorry. The feedback loop, in case of Google's algorithms, contains only a single score, 20% accuracy. That's the only thing I can get from the model design and training process. But because now you see the entire training data set, you see the entire validation data set, you can actually get the feedback at individual example level. So think about the validation set with 1,000 examples. For each example, you know your classification result is correct or not. That's a lot more information than average number, average accuracy. So here you got 1,000 different numbers. That's a better feedback. So you know that the new design that I generate worked better on some examples, but worse on other examples. So that's the information. So that's the information that allows you create a new design much faster. So with this improvement, we created our own algorithm called the generalized architecture search. Kind of similar to the name that Google used for their reinforcement learning algorithm, which they call a neural architecture search. The reason we call it generalized architecture search, the term generalized coming from the fact our methods support both neural net and the traditional machine learning. In case of traditional machine learning algorithms, the architecture search is actually referring to the fact that we have to define what kind of features should be extracted from the data. Most of the features can be defined as functions over one or multiple columns. If you think about your input data set table, so each column are the attributes or features that the user feed in. So the new features have to be defined on those inputs. But there are many ways to do those feature extraction to generate new features. And especially if this feature extraction takes 2 inputs, then you have a combination problem. And some feature actually takes 3. So the generalized architecture search also solves this problem by figuring out which algorithm should be applied to which columns to generate new features. That makes the algorithm work much better. So that's why basically I'm saying this one also has automated feature engineering. And the same logic can be applied to deep learning also. It's not actually limited to traditional machine learning algorithms. And because the introduction of a validation set to the controller can take a look at the data before generating first design. So it only needs to generate much fewer models in order to get a reasonable solution. So in reality, we limit the number of models that we train to something like 20 to 30 models. And for that, we got reasonable results. And from our real customers' feedback, most of the time, those models are better than human designed models. If we allow it to run longer, to generate more models and get more feedback, the model will be even better. This algorithm is what powers OneClick.ai, the platform, the deep learning, the automated deep learning platform that we built. Okay, now I have 3 or 4 slides talking about this platform, if you are interested. So the basic idea of this, as I explained earlier, is to use AI, essentially to use our own supervised learning algorithm to take a look at your data to design the algorithm or models for the data that you uploaded. So every model we build is actually customized for your data. We don't just use a generic algorithm and do parameter tuning. And because the model design can be iteratively improved, so the first model you see may not be the best one, but over time it will going to see better and better model. And the amount of time we're talking about typically range from, let's say, 10 minutes to up to a day, unless you have very large image data sets. Comparing to what Google could offer, our platform runs on much fewer machines and produces results much faster. That makes it a lot cheaper actually to use. That's why basically we are the only automated platform that can offer free trial. And because we use deep learning, because we do automated feature extraction, so we can support a much larger variety of data as input. So numerical data, traditional numerical data, categorical data, and data time series, and text, images are all supported. And you can actually combine many of them together. You can build a classifier that takes 2 images, 3 text columns, and numerical data as input to build a single classifier. That's why basically I was talking about saying this is a very generic solution. And right now, the type of solution we support are regressions, basically predicting numerical numbers, and classifications, and time series forecasting. Time series forecasting is not much different from regression, except there's time series involved. And we actually also support clustering and recommendation. And vision is just a special case for classification. It's when you have single image as input and you want to classify into something, you call it vision application, but it's just a special case. And by the way, for the classification, we support all the 3 common type of classifications: binary classification, multi-class classification, and multi-label classification. And in case of vision, for example, if you have single image as input, and if you are doing multi-label classification, you're essentially doing object detection, because you can detect whether the image contains a dog or a cat or both of them. And to our users, the key thing is because we were able to automate feature extraction and model design altogether, we can make this plan super simple to use. Our users don't have any technical background. That's the consequences. Without this technology, You can automate the engineering part of the machine learning, but you cannot automate the model design. You cannot automate feature engineering or data cleansing or many other things. Because those things, in order to do those things manually, you actually need to understand the algorithm to some degree. So that's why basically we automate the entire thing using technology that we have, so that the user don't need to know how the model algorithm works at all. With this technology, we make our platform as simple as Excel, actually much simpler than Excel. If we have time to give a demo, you can see actually there are only a couple of buttons, and most of the functions are accessed through chatbot. The reason we have chatbot in a machine learning platform, which is kind of weird to most people, is the chatbot can hide complexity. So if you are a machine learning expert or has the know-how, you may want to ask a question like, what's the, let's say, in case of binary classification, you may ask what's PR curve look like, or what's the ROC. We can show those information, but we don't show them by default, so that we can keep things really simple, that people without AI background can comfortably use it. But if you know those information, you can simply ask in natural language. We will answer it, and we will show the chats for you. So that's pretty much all about this talk, and I'm happy to take questions.
Sure, demo something like that.
Definitely, I can do it.
There's some questions online.
Okay, so let me take a
check.
I'm zoom this one. Chat. How I'm supposed to? Okay. Okay. I hope they figure out how to hear us. Okay, awesome. Lots of AutoML free to. If you're talking about Google AutoML, it's not free to use. For each single model, they charge $500 right now, and it's like a trial account. But based on the cost that they have, eventually they will have to charge more. Of course, but it's Google; they can afford to offer everything free. Yes, in theory, when it comes to the reinforcement learning model, let me show you. In theory, this one can represent any model that you want, because this is a general solution to define a graph. A graph are just a set of operations and interconnected by connecting the output of one operation as the input of another one. If you have, essentially it's a directed graph. So, but any directed graph can be described by a linear specification. Think about this as a language defining a graph. That's the power of the expressiveness. So in theory, this can define any neural net. But in practice, it doesn't work that well. That's why basically Google has built in heuristics to limit its choices and restricted those parameters to certain things. For example, in this particular design, they restrict those parameters to the parameters of convolution layers. Those restrictions is what made this algorithm to work in practice. Without those restrictions, I highly doubt it's going to be able to build a image classifier better than Hillman. So, any data perspective for regression? I'm not really sure what the question means.
Can you read the question?
Any data spec tips for regression X classification? So I don't understand the question here. Yeah. So wouldn't the model be biased if it looks at validation dataset first? That's why it's a validation dataset. It's not a test dataset. So in our implementation, when user upload the dataset, we have to split it into 3 subsets. The first is the test set, which results 20% as test set. This dataset is never looked at all. It's only used after we train the model, and it's not used to improve the model design. The validation set is what we reserve as another 20% of whatever left in the training data. We use this 20% of data to improve the model design. That's why basically we can look at the validation set, but the metrics reported to the user in the very end are based on the tested set. So validation set is only used for model design. That's why that's why the model might be slightly biased, but when we report the metrics are not biased, and that's what is most important. Do you have any example of how good the result is? We did some comparison on some data sets. Because our aim, right now we limit our models to up to 30 models. So I don't expect on every data set we have the best results beating human designs. But because as time when we did a comparison, we actually compared with Google AutoML and the Microsoft Custom Vision API. Sorry. Some of your guys are from Microsoft. So Microsoft released a product called Custom Vision API that allow you to upload small data sets and build an image classifier. And Google AutoML is only allow you to build image classifier too. So we did a comparison using small image data set to build image classifiers on all the 3 platforms that we can find.